So my work was to present the first look at code obfuscation for WebAssembly. Our primary motivation for the study was to provide a preliminary evaluation of WebAssembly obfuscation and evaluate how effective that obfuscation was from two different perspectives, are shown there, dissimilarity and detectability. I'll go more in depth on those later on. For those of you who don't know, WebAssembly is a compilation target for high-level languages within browsers that facilitates the creation of high-performance web applications. It does this using a low-level bytecode running in browsers that is not really similar to assembly, but it is a machine code that gets eventually compiled within the browser to binary. And it's extremely efficient since it is performance-oriented, and it is commonly used in IoT and edge computing, and because of its performance, it is very effective on mobile devices and other hardware-constrained devices. Because of that performance orientation of WebAssembly, one of its main uses is cryptojacking malware. So, as you can see on the right, the majority of WebAssembly instances found in the wild in the top million Alexa websites are malicious instances of WebAssembly. Because WebAssembly has access to the entire JavaScript context and it purely runs within the browser, not creating any system calls or anything similar to that, it means that any malware can run without being detected by a native antivirus. So because of the platform independence, meaning it can run on iOS, Android on its own as its own operating system or within browsers, it has also allowed malware authors to target multiple different devices at once without having to tailor malware for those specific devices. On the other hand, obfuscation there's two main forms of obfuscation. The first is control flow obfuscation, which is done by modifying the control flow graph of a program. It is effective, it is usually commonly applied at the highest level of program, being source code, so say C, C++, or Rust in the context of WebAssembly. And then as the program is compiled, those control flow obfuscations tend to follow through to the binary level. These forms of obfuscation can be resistant to both static and dynamic analyses, which are the common way to analyze a program. Data obfuscation, on the other hand, is an attempt to make data harder to decipher. Often it is more effective at the higher level. Say, if you have a variable, you can just, a very primitive data obfuscation would be to just change the name of the variable. But as you compile and get to the binary level, those obfuscations tend to be abstracted away. But sometimes control flow obfuscations can result in data obfuscations or vice versa. Here's an example of the original control flow of a program, and the obfuscated one underneath is a variety of different obfuscation techniques. Traditionally, a program is obfuscated using an obfuscator, which is a program that takes in a source code or a piece of unobfuscated code and will apply obfuscation to it in an automated manner that it would not be realistic for a human to do so. So our approach for obfuscating WebAssembly and measuring it started with the threat, right? A malware author charging the WebAssembly platform can hide the code in one of two methods using obfuscation. The first is to use an existing high-level obfuscator. We think this is the most realistic because, one, obfuscators that are made for high-level languages like C and C++ tend to be more complex and be able to apply obfuscation techniques that aren't really primitive. And second, they're easily and readily available. Some of them are free, some of them are paid for, but obfuscators like Stunix and like Tigris are pretty commonly used and well-known. The second option is the more unrealistic one, which is to create a low-level obfuscator for the WebAssembly language itself. WebAssembly is a language of its own. It is a machine code that runs on a stack machine, and it's not really similar to any other existing language, so no obfuscation technique can be applied to it. Many people think obfuscation techniques that have been applied to traditional assembly or x86 assembly can be translated to WebAssembly, but this isn't the truth because assembly or traditional forms of assembly run on a register machine, which means gives you access to things like jumping to the function table and things like that, or jump to other sections of code. These things don't exist in a stack machine, meaning that we can't adapt those methods to use for WebAssembly. We also think it's unrealistic for a malware author to create a novel obfuscator for the sole purpose of obfuscating their malware when they can do so with their source code that they'd be compiling from. So for that reason, we chose to start with the C language because that is C and C++ are two most commonly used languages for WebAssembly, source languages. And we used the Tigris obfuscator. We chose Tigris as the obfuscator of choice because of its rigorous testing in the literature and its availability of various obfuscation techniques. We chose the 7 techniques listed there based off of their appearances in the literature and how, for example, opaque predicates has been rigorously tested and it tends to be the standard obfuscation techniques most studies would apply. We also wanted to measure if obfuscating at the highest level, at C, C++, Rust, etc., can carry through to the WebAssembly machine code or the binary level. So by applying our obfuscation at the highest level, it allowed us access to complex obfuscation techniques, as well as our ability to measure what effect the compilation process has on these WebAssembly programs. We did this by using a data set consisting of C source code Wasm applications. These are applications that are written specifically for WebAssembly, but the source language is written in C. And then we split the data set into two parts. The original unobfuscated programs in the data set are compiled as they normally would. The compilation process for WebAssembly is it starts with the source code, goes through a compiler called mscript, or you can use multiple compilers, but the compiler of choice is mscriptin for most WebAssembly development, which results in a Wasm module. This Wasm module can then be inserted into a web page and instantiated in the browser with JavaScript, which triggers the second compilation process within the browser, which is a two-tier compilation process that changes depending on the context of, is it running on mobile, is it running on iOS, is it running on Android, etc. On the other hand, on the other side of the pipeline, we inserted our unobfuscated source code into an obfuscator, applied the obfuscation techniques, leaving us with 7 new samples. Each of these samples is an obfuscated version of the original code, corresponding code in the data set, and then it went through the same process below. It went through the mscriptin compiler, we were given a Wasm module, and then it was inserted into a web page, instantiated, and compiled. At these two different stages, the Wasm module stage and the Wasm binary stage, we compared each of the 7 obfuscated WebAssembly programs to their original unobfuscated counterpart in an attempt to analyze it and see what effect the obfuscation had and how the compilation process affects the obfuscation. There's 2 ways that we evaluated the performance of obfuscation. The first was, or before we get there, first let me go over what the data set looked like. This was the breakdown of our data set. These were the main categories of WebAssembly programs. Almost all of them can fit under either games, libraries, applications, or cryptojacking malware. We had a small data set, as you can see, but the reason for that is because we wanted to make sure we had a realistic data set. We could have just chosen any C program and obfuscated it, but instead we wanted programs that were made for WebAssembly, used in the wild, and could be effectively obfuscated using our obfuscator. All of the samples that we chose also run on mobile devices without any performance impact or performance loss. We could have chosen applications that could only run natively on Windows or on a browser on a desktop. But oftentimes, there can be programs made for WebAssembly that can't run on mobile devices. But since cryptojacking often targets mobile devices as well, we wanted to make sure that we included programs that are compatible with running on mobile devices. Our cryptojacking samples, as you can see, we have a relatively small cryptojacking set. It's only 2 samples. This was limited for 2 reasons. The first is because many cryptojacking malwares their source code is written in C++. That's if their source code is released. We need the source code to be able to obfuscate it. Oftentimes, you can pull just the Wasm module, but we can't really do much with that. The second is that for samples that were written in C, sometimes they use libraries that weren't compatible with our Tigris obfuscator. Of course, you can make your own obfuscator that would be able to be compatible with those libraries, but that was out of the scope for this study, as it was just a preliminary evaluation of the effect that obfuscation can have. Once our dataset was obfuscated, you have the breakdown here. This is including for every original sample we had 7 new samples, each of them being individually obfuscated. Each of the original 15 programs that we had obfuscated 7 different ways, which led us to a total dataset of 120 programs. The first way that we evaluated obfuscation was through similarity or dissimilarity. Because the end goal of an obfuscation is to produce a dissimilar product or a dissimilar program, we chose to measure the similarity between our unobfuscated and obfuscated programs. There are many different ways to do so, many different metrics that you could use to measure. Historically, in obfuscation literature, there were 3 metrics that people used. These are 2 common ones. The first is complexity metrics, like McCabe or McCabe cyclomatic complexity number or things like that. These were originally measures of program structuredness and used variables like amount of lines of code and amount of variables used and things like that. We don't think that's a very reliable metric. It's not very reliable in terms of different languages or different minor edits in code can result in a very different cyclomatic number. It also can't be applied to low-level languages like machine code or binary because it is reliant on things like having high-level abstract ideas of functions, variables, etc. It's an outdated metric that hasn't been used in a while. The other common metric is cost metrics, which are just space and time overheads. This is very hard to use for WebAssembly since WebAssembly is very dependent on the hardware it's being run on. using cost, like space or performance as a metric for comparing a mobile device's cryptojack malware versus a native like desktop malware isn't really realistic, since platform independence is something that WebAssembly prides itself on. It also doesn't reveal any meaningful insights. There's no way to know how effective the obfuscation was. For all I know, it could just make the program slower. It's not a reliable method either. So we chose to go with the third most common method, which is similarity. Cosine similarity is the similarity metric that we chose to use. It is a good way to measure how similar or dissimilar machine code is. And we did so using cosine. The reason we use cosine similarity is so that we could use n-gram analysis. We think cosine similarity is the best form of similarity metric that we can use because, say, for example, Euclidean distance. And trying to take the measure of Euclidean distance between an obfuscated and unobfuscated program, say that just the program, the obfuscation added 20 lines of code at the bottom of the unobfuscated program. The Euclidean distance would be high, but that program is still similar, because if I put 20 print statements at the bottom of a whole program, the program is still functionally doing the same thing. I might just print something 20 times. But cosine similarity would allow us to offset that, allow us to see, even including length as a metric, it would allow us to be able to see how similar the program itself is, regardless of things like that. We also use CF-IDF vectors to for our n-grams to offset any difference in length or things like that. And we use n-grams because since WebAssembly runs in a stack machine, it allows us to see and measure the line that or operation that came before it or after it. Because WebAssembly is just a series of pop and push operations, the order in which those operations are executed matters a lot. It's extremely important. So that's why n-gram analysis is vital to be able to measure WebAssembly obfuscation. These are the results of the similarity. We took the average in each category of program, and to the left, we have listed each obfuscation technique. For each bar, lower is better. This is a measure of similarity. So the closer it is to 0, the more dissimilar it is. As you can see, there isn't any real pattern to the data besides that alias disruption is effective regardless of the category of program. But the one thing that is noticeable is that with the exception of taint disruption for applications, almost every single obfuscation technique resulted in the binaries having a cosine similarity of less than 0.5. 0.5 tends to be the threshold for what is similar and dissimilar. You know, we can categorize every obfuscation technique, again, except for taint disruption, as producing dissimilar binaries. This is just the graph for binaries. So the implications of that are that high-level obfuscation techniques directly obfuscate the Wasm binaries. There is a correlation, and it is a direct result of the obfuscation that we applied at the highest level, in this case, the C level. The majority of our obfuscation techniques were successful with similarity being less than 0.5, and there is no one best technique. If you look, it depends on the category of program. While taint disruption might be the best for libraries, it obviously is not the best for applications. The obfuscation and the effectiveness of the obfuscation is reliant on what type of program is being obfuscated and the content of that program, which means there is no one golden bullet for obfuscating WebAssembly. But while we've arrived at the conclusion that obfuscation can result in dissimilar machine code and binaries, that doesn't mean we can conclude that the obfuscation was successful. A successful obfuscation, in the context of, say, malware, would be that the obfuscated program is not caught by an antivirus. So we tested exactly that. We tested the detectability of those cryptojacking samples. Traditionally, and even in the context of WebAssembly, there are two ways to detect and analyze WebAssembly programs. The first is through static analysis, no surprise. It analyzes the program's file. These forms of analysis tend to be more lightweight because it's simply checking the file. This is also the most popular option for cryptojacking detection because oftentimes these have to be run within a browser without having a large performance impact. And this can take many forms, including learning-based methods, string matching, fuzzy hashing, etc. This is also, these defense mechanisms tend to be written for mobile devices as well, so they tend to be very efficient. On the other hand, dynamic analysis requires running the program, requires computation, and creates a performance overhead that isn't realistic for cryptojacking detection methods to have on hardware-constrained devices and mobile devices. So common dynamic analyses like taint tracking and memory access tracing are not realistic to be implemented for mobile devices. And in the literature, while these methods do exist for WebAssembly, they would never be implemented as a method in real time to detect cryptojacking samples. Instead, we use MINOS. which is a deep learning-based static analysis detection method that uses a convolutional neural network to analyze binaries of WebAssembly files and categorize them either as malicious or benign. It analyzes these grayscale images using the pattern shown to the right. This pattern is the standard pattern that binaries of cryptojacking malware use. It is a 98.97% accurate, or 99% accurate, cryptojacking detection method that can and has been run on mobile devices without creating a significant performance overhead, meaning it is realistic to use in the wild. It was published in NDSS and has been rigorously tested in the literature. What we did is we fed all of our samples, all 120 samples, including the unobfuscated and obfuscated, into Minos. The graph is shown to the right, and while it might be a little hard to tell what's going on, if you notice there are two rows that are in red. That first column is the unobfuscated. Minos detected our cryptojacking samples when they're unobfuscated and correctly categorized them as malware. But then once we obfuscated them, almost every single obfuscation technique bypassed Minos, meaning all of our cryptojacking malware, with the exception of one technique using flattening on one of our samples, was able to trick a previously 99% successful and accurate cryptojacking detector. Our cryptojacking obfuscation was 93% successful, and then any other of the obfuscated samples, any other sample that was detected as malware was almost always incorrect, creating a 70% false positive rate, which rendered Minos completely ineffective. This showed us that obfuscation for Wasm binaries for malware can be successful in the wild. And even though we only had 2 cryptojacking samples, we think that analysis can be extended to more than just those 2 because they were built on Kryptonite, which is a hashing algorithm that's very commonly used for Monero miners, which is the main type of crypto miner used in the wild. So our benign samples were also being flagged as malicious, which renders learning-based detection systems like Minos. There's more than just Minos that uses that similar detection method of analyzing the Wasm module or the binaries and categorizing them as benign or malicious. We know for sure that it will render those forms of static analysis ineffective. But we can also conclude that there are other forms of static analysis that the same way, because we're changing what the binaries look like, that they will end up also being ineffective. Our results can be generalized to other cryptojackers, which I already mentioned. Kryptonite is the basis for the majority of cryptojackers found in the wild, and those were the 2 cryptojackers, or the 2 cryptojackers that we use were also built on Kryptonite. Which leads us to some concluding thoughts. Here, our contributions were that we presented the first comparative analysis of multiple obfuscation techniques for WebAssembly across a variety of different Wasm-based web applications and mobile applications. This was, again, just a preliminary introduction to what obfuscation can do for WebAssembly. We've also demonstrated how obfuscation can affect how the obfuscation of Wasm web applications can affect these static analysis tools like Minos and their ability to discriminate between benign and malicious web programs. So we presented the first analysis and evaluation of obfuscation for WebAssembly. High-level obfuscation has been proven to be effective in producing dissimilar binaries, and obfuscated Wasm malware can bypass status quo detection methods, which poses a significant threat to IoT networking and mobile devices, since it is the first time, or not the first time, but Wasm is being used very commonly to create a platform-agnostic virus, like cryptojackers, that can run regardless of the native operating system. These are references. Thank you for your attention.
Thank you. So, are there questions from the audience? Yes, there's one.
Hi, this is Jiska. Thank you for the talk. I would like to know, have you looked into obfuscation beyond malware? Like, if a company wants to protect their intellectual property.
So if we go back to here, all of our samples, including the libraries, the games, the applications that we have up top, they were all obfuscated. So we have the similarity results in terms of how dissimilar the categories are listed down here: applications, games, libraries, etc. So looking beyond cryptojackers, we had a more comprehensive data set for things that weren't malicious, for things like applications and games and libraries. We can see the obfuscation is still successful, and then when it comes to, say, trying to reverse engineer it or looking at patterns, you can tell that the obfuscation clearly disrupts the patterns since it creates a false positive rate where benign programs, or originally benign programs, are being flagged as malicious. So yeah, it would be pretty effective on even benign programs to deter software reverse engineering. Yeah.
Thank you.
Thank you. Excellent talk. Forgive me if I missed this. My understanding is that you took the obfuscation in the original source code.
Yes.
And then you saw the effects in the Wasm code.
Yes.
Did you see if you had similar effects if you would have compiled it to native directly? So it's basically, is this an artifact of it's a really good obfuscator, or is this something specific to the implications of using Wasm on top of that?
So there have been previous studies in the past that analyzed the effect of our obfuscator in specific on native binaries. And while it was successful, what we wanted to measure was the difference between the Wasm compilation process in the context of its browser compilation process. While we can obviously check the Wasm module that's included in the web page, we can analyze the machine code there. Because of the two-tier compilation process that every Wasm program uniquely goes through, we wanted to see, can the obfuscation carry through that? And it's also because of those pre-existing studies of using native binaries to measure compilation, or to measure obfuscation, we wanted to see, since WebAssembly doesn't run like how a native program would in a registered machine during its compilation process using traditional assembly or something adjacent to it, we want to see the effect that using a stack machine, which is what WebAssembly uses, had on those obfuscation techniques. Because a lot of them might be optimized away or be gone completely when using a stack machine.
So was it more, less, or equal?
It was roughly equal.
Roughly equal.
Yeah.
Okay.
Great talk. Just a quick, maybe a clarification question. You showed results for similarity in machine code.
Yes.
Did you study the similarity in terms of control flow? So,
So like recreating the control flow graph so there are no tools readily available to pick apart, say, the machine code or the Wasm module to be able to recreate a control flow graph from that code. If those tools were available to us, then we would have done that. But to create that tool would be out of the scope of just what is really a preliminary evaluation of the performance and the effect that obfuscation has on WebAssembly.
But that would give better insight on why.
Yes. So based off of the results that we have, we think that if we were to recreate the control flow graph based off of the Wasm modules or the binaries that we measured with the similarity listed here, the control flow graph would look extremely different than the unobfuscated program. Because
that is an intuition right now.
Yeah.
Right.
So if there is a program to reverse engineer Wasm modules because they are just machine code, and then recreate that control flow graph.
But there are tools that also use a control flow graph and the differences, the minor differences to kind of still detect.
Yeah. So a lot of those tools that we saw they were forms of dynamic analysis that would be not realistic for us to use as a metric like this when we have other metrics like detectability. That would be a much more realistic metric to use practically for software developers. And a lot of the ones that traditional ones that take in a file and just produce the visualized control graph from it. Well, we could do that with the source code, and it would obviously produce a radically different control flow graph. There is no, because Wasm is such a new technology and it's a new language, there aren't a lot of those reverse engineering tools that are available yet for us to be able to apply to our Wasm machine code. There are those that can be used for the binaries because the binaries are just binary, but those tend not to be the most reliable because depending on the platform that our Wasm machine code is compiled on, whether it be mobile or desktop, it can produce radically different binaries.
Thank you.
Thanks a lot. So, thank you a lot for your presentation. Applause to the speaker again.